We're about to embark on a journey through some of the most mysterious and breathtaking visitors our solar system has ever known. Picture this for a moment. You're standing in your backyard on a clear winter evening, gazing up at the star-studded sky, when suddenly you notice something that shouldn't be there. A fuzzy star with what appears to be a glowing tail stretching across the darkness. Your heart races as you realize you're witnessing something that humans have marveled at for thousands of years. Something that has inspired both terror and wonder throughout our entire history. You're looking at a comet. Tonight, we're diving deep into the fascinating world of these cosmic time capsules. These ancient messengers from the very edges of our solar system that carry secrets from the birth of everything we know. We'll explore the most famous comets that have graced our skies, uncover the science behind their spectacular displays, and discover why these dirty snowballs might hold the key to understanding how life itself began on Earth. If you find comfort in these gentle explorations of our cosmic neighborhood, I'd be grateful if you'd consider subscribing and giving this video a like. The visuals are here to guide you, but feel free to close your eyes, take a deep breath, and let your imagination soar through the solar system alongside these magnificent wanderers. I'd love to know where you're watching from tonight. Drop your location in the comments below. So what exactly makes a comet so special? Why do these seemingly simple chunks of ice and rock capture our imagination in ways that asteroids and meteors never quite manage? The answer lies in their incredible journey and the spectacular transformation they undergo as they venture into the inner reaches of our solar system. Comets are essentially frozen relics from the very dawn of our solar system, formed over 4.5 billion years ago, when our sun was just beginning to shine and the planets were still taking shape. These cosmic time capsules have spent most of their existence in the frigid outer darkness, far beyond the orbit of Neptune, preserving within their frozen cores the original materials that existed when our solar system was nothing more than a swirling disk of gas and dust. Think of comets as nature's own deep freeze, storing samples of the primordial ingredients that would eventually become planets, moons, and perhaps even the building blocks of life itself. They're like cosmic archaeologists, carrying with them evidence of conditions that existed when Earth was just beginning to form, when the first organic molecules were coming together in the cold depths of space. But here's where the magic truly begins. When one of these ancient wanderers gets nudged from its distant home, perhaps by the gravitational influence of a passing star or the subtle pull of our giant planets, it begins an epic journey toward the inner solar system. And as it approaches our sun, something absolutely remarkable happens. The comet begins to wake up from its billions-year slumber. The sun's increasing warmth starts to work on the frozen nucleus, and the comet begins its spectacular transformation from a dark, invisible chunk of ice and rock into one of the most beautiful sights our solar system has to offer. This process is called sublimation, and it's what creates the breathtaking displays that have captivated humanity since we first looked up at the night sky. As the comet ventures closer to the sun, its frozen gases begin to vaporize directly from solid to gas, bypassing the liquid phase entirely. Water ice, carbon dioxide, carbon monoxide, methane, and ammonia all start streaming away from the nucleus, carrying with them countless tiny particles of dust and rocky debris. This creates what we call the coma, a massive atmosphere that can grow to be hundreds of thousands of kilometers across. sometimes becoming larger than our Sun itself. But the coma is just the beginning of the comet's magnificent display. The real showstopper is the tail, or more accurately, the tails, because most comets actually develop two distinct tails as they approach the Sun. The pressure of sunlight itself and the stream of charged particles flowing out from the Sun, called the solar wind, begin to push this newly formed atmosphere away from the comet, creating the iconic tail that can stretch for millions of kilometers through space. The dust tail forms as radiation pressure from sunlight gently pushes away the tiny solid particles mixed in with the vaporizing gases. This tail has a slight curve to it, following the comet's orbital path, and often appears yellowish or white as it reflects sunlight like countless microscopic mirrors scattered through space. The ion tail, composed of electrically charged gas molecules, responds more dramatically to the solar wind. This tail points straight away from the Sun like a cosmic windsock, often glowing with a beautiful blue color as the ionized gases emit their own light. What's particularly fascinating is that these tails always point away from the Sun, which means that as a comet travels away from the Sun after its closest approach, it's actually preceded by its own tail, racing ahead of it through space. This creates one of the most counterintuitive aspects of comet behavior. Unlike a rocket or airplane that trails exhaust behind it, a comet departing from the inner solar system is essentially being chased by its own nucleus, with its magnificent tail leading the way into the darkness of the outer solar system. Now, you might wonder where these cosmic wanderers originate. The answer takes us to two of the most mysterious and distant regions of our solar system, places so far away that no human spacecraft has ever visited them. Yet they profoundly influence the spectacular displays we see in our night skies. The first of these regions is called the Kuiper Belt, a vast ring of icy objects that begins beyond Neptune's orbit and extends roughly 50 times farther from the Sun than Earth. This region is home to dwarf planets like Pluto and countless smaller objects composed largely of frozen water, methane, and ammonia. The Kuiper Belt is thought to be the source of short-period comets, those that complete their orbits around the Sun in less than 200 years. But even more mysterious is the Oort cloud, a theoretical sphere of icy objects that may extend nearly halfway to the nearest star. This vast reservoir, named after Dutch astronomer Jan Oort, who first proposed its existence, has never been directly observed because its objects are simply too far away and too faint to detect with our current technology. Yet we know it must exist because of the long-period comets that occasionally venture into the inner solar system, some taking thousands or even millions of years to complete a single orbit around the Sun. The Oort cloud represents the very edge of our Sun's gravitational influence, a twilight zone where the faint pull of our star battles with the gravitational effects of nearby stars and the galaxy itself. Objects in this distant realm exist in a state of perpetual near darkness, receiving virtually no warmth from our Sun, frozen solid at temperatures approaching absolute zero. Occasionally, something disturbs one of these distant objects. Perhaps a passing star tugs on it gravitationally, or the subtle influence of the galaxy's rotation shifts its orbit ever so slightly. When this happens, the object begins its long, slow fall toward the inner solar system, a journey that may take millions of years to complete. This journey from the Oort cloud explains why some comets appear completely without warning, blazing across our skies with no prior notice. Unlike the predictable returns of short-period comets from the Kuiper belt, these long-period visitors from the Oort cloud follow such elongated orbits that their previous visits may predate human civilization by thousands or even millions of years. Understanding these distant origins helps us appreciate just how special every comet sighting truly is. Each comet represents a messenger from the very edge of our solar system's influence, a traveler that has journeyed across distances so vast that light itself takes months or years to cross them. When we see a comet in our night sky, we're witnessing the culmination of an epic voyage that began in the frozen darkness beyond imagination. The composition of these cosmic visitors tells us incredible stories about the early solar system. Comets are often described as dirty snowballs, though recent research suggests they might be better characterized as icy dirt balls, containing more rocky material, mixed with various types of ice than originally thought. This mixture of ice and rock preserves a record of the conditions that existed when our solar system was forming, making every comet a potential library of information about our cosmic origins. The ices in comets aren't just frozen water. They contain carbon dioxide, carbon monoxide, methane, and ammonia, along with more complex organic compounds that form the building blocks of life as we know it. When these materials sublimate and create the comet's magnificent display, they're essentially revealing the chemical inventory of the early solar system, showing us what ingredients were available when Earth was forming. This brings us to one of the most profound questions in all of science. Did comets play a role in bringing water and the organic compounds necessary for life to our young planet? Some scientists believe that during a period called the Late Heavy Bombardment, roughly 4 billion years ago, countless comets and asteroids rained down on the inner planets, delivering vast quantities of water and organic materials to Earth's surface. However, recent detailed analysis of comet composition has revealed a more complex story. The ratio of heavy hydrogen to regular hydrogen in many comets differs significantly from that found in Earth's oceans, suggesting that comets weren't the sole source of our planet's water. This discovery has led scientists to consider multiple sources for Earth's water, including comets, asteroids, and water that may have been trapped within Earth during its formation. As we continue our journey through the most remarkable comets our solar system has to offer, we'll discover how these ancient wanderers have shaped human history, inspired scientific breakthroughs, and continue to surprise us with their beauty and complexity. From the predictable return of Halley's Comet to the unexpected splendor of recent visitors like Neowise and the spectacular disintegration of C2024 G3 Atlas, each comet tells its own unique story of cosmic evolution and the delicate dance of gravity that governs our solar system. The story of comets is ultimately the story of our own origins, written in ice and dust across the vast expanses of space and time. Let's begin with perhaps the most famous comet in human history, one whose return has been documented for over 2,000 years and whose predictable appearances have both terrified and fascinated civilizations across the globe. This is Halley's Comet, a celestial timekeeper that visits our inner solar system every 76 years like clockwork, carrying with it stories from ancient China to modern space exploration. Picture yourself as an astronomer in 1705, working by candlelight with nothing but mathematical calculations and historical records. This was the world of Edmund Halley, who made one of the most remarkable discoveries in the history of astronomy. While studying the orbital paths of several bright comets that had appeared in previous centuries, Halley noticed something extraordinary. The comets observed in 1531, 1607, and 1682 seemed to follow remarkably similar paths through the sky. Using Isaac Newton's revolutionary theories of gravitation, Halley made a bold hypothesis. What if these weren't three different comets at all, but rather the same cosmic visitor making regular return trips to the inner solar system? The implications were staggering. If Halley was correct, this would be the first known periodic comet, and he could actually predict when it would return. Halley calculated that the comet would next appear in 1758. It was a prediction that would take 53 years to verify, long after Halley himself had passed away. But when 1758 arrived, astronomers scanning the skies were rewarded with the sight of the predicted comet, blazing across the heavens exactly as Halley had foretold. This moment marked the birth of predictive astronomy for comets and established Halley's Comet as the first member of an exclusive club of periodic visitors. The physical characteristics of Halley's Comet reveal fascinating details about the nature of these ancient wanderers. The nucleus, the solid heart of the comet, measures roughly 15 kilometers long and 8 kilometers wide, about the size of a small mountain. But here's what makes it truly remarkable. This mountain-sized object is one of the darkest things in our entire solar system, reflecting only 3% of the sunlight that strikes it. This incredibly low reflectivity initially puzzled astronomers. How could something made largely of ice be so dark? The answer lies in the comet's long history of solar encounters. Each time Halley ventures close to the Sun, its surface ices sublimate away, leaving behind a layer of dark, rocky material that accumulates over thousands of years. This creates a kind of cosmic suntan, a protective crust that helps preserve the pristine ices beneath while giving the comet its characteristic dark appearance. The orbit of Halley's Comet is a study in cosmic extremes. Its highly elliptical path takes it from well inside the orbit of Venus at its closest approach to the Sun, out to beyond the orbit of Neptune at its farthest point. This means that during each 76-year cycle, Halley experiences temperature variations that would challenge any earthly environment, from the searing heat near the Sun to the frozen darkness of the outer solar system. When Halley returned in 1986, humanity was ready with something unprecedented in the comet's long history of visits. For the first time, we sent spacecraft to intercept this ancient traveler, providing our first close-up views of a comet nucleus. The European Space Agency's Giotto mission, along with several other international spacecraft, revealed that comet nuclei are far more complex and varied than anyone had imagined. The images returned by Giotto showed a world of incredible contrasts. While most of Halley's surface appeared inactive and dark, certain areas erupted in brilliant jets of gas and dust as the sun's heat penetrated the insulating crust. These active regions, covering only about 10% of the nucleus, were responsible for creating the comet's entire magnificent display, demonstrating just how efficient these cosmic engines can be at transforming stored solar energy into spectacular celestial theatre. But Halley's Comet represents just one type of periodic visitor. To truly appreciate the diversity of comets in our solar system, we need to journey to more recent times and witness one of the most spectacular comet displays of the modern era. In July 1995, two amateur astronomers working independently on opposite sides of North America made discoveries that would change our understanding of what comets could achieve. Alan Hale, observing from New Mexico, and Thomas Bopp, scanning the skies from Arizona, both spotted the same fuzzy object in the constellation Sagittarius. What they had found was remarkable not just for its discovery, but for its incredible distance from the Sun. Most comets at such distances, beyond the orbit of Jupiter, remain invisible to ground-based observers, showing no activity whatsoever. But this comet was already displaying a clearly visible coma, suggesting something truly extraordinary was approaching. Comet Hale-Bopp, as it came to be known, would go on to become one of the most observed and photographed comets in human history. Its nucleus, estimated at 60 kilometers in diameter, was roughly 6 times larger than Halley's, making it a true giant among comets. This enormous size explained why it could be seen from such vast distances and hinted at the spectacular display it would eventually provide. As Hale-Bopp continued its approach toward the inner solar system, astronomers around the world trained their instruments on this cosmic giant, documenting its evolution in unprecedented detail. The comet's dust production rate reached extraordinary levels, ejecting over 2 million kilograms of material every second at its peak activity. This created a coma so dense that it may have become optically thick, meaning that the inner regions became hidden behind their own dust production. What made Hale-Bopp particularly special was its extended period of visibility. Unlike most comets that remain visible to the naked eye for only weeks or months, Hale-Bopp remained a naked eye object for an astounding 18 months. This marathon visibility meant that people who missed its initial appearance had multiple opportunities to witness its glory, and it became visible from both northern and southern hemispheres at different times during its passage. The scientific observations of Hale-Bopp yielded numerous important discoveries about comet composition and behavior. Astronomers detected the smallest dust grains ever observed from a comet, particles that glowed with high temperatures and showed strong emission features, indicating their silicate composition. The comet also displayed the highest linear polarization ever measured from any comet, providing new insights into how dust particles interact with sunlight. Perhaps most intriguingly, Hale-Bopp's orbital history suggests a dramatic past. Calculations indicate that its previous visit to the inner solar system occurred roughly 4,000 years ago, around 2215 BC, during the reign of Pharaoh Pepi II in ancient Egypt. Some evidence suggests this may have been the comet's very first journey inward from the Oort cloud, possibly triggered by a near encounter with Jupiter that dramatically altered its orbit and sent it on its current path. The comet's composition revealed important clues about conditions in the early solar system. Like many long-period comets, Hale-Bopp showed a high ratio of heavy hydrogen to regular hydrogen, much higher than the ratio found in Earth's oceans. This discovery was crucial in helping scientists understand that comets alone could not account for all the water on our planet, suggesting that Earth's oceans formed from multiple sources during our planet's violent early history. Moving forward in time, we encounter another remarkable visitor that graced our skies more recently. In March 2020, during a time when much of the world was focused on earthly concerns, astronomers using the NEOWISE space telescope made a discovery that would soon capture global attention. What they found was a comet that would become known as NEOWISE. and it would provide the first spectacular comet display visible from the northern hemisphere in over 20 years. Comet Neowise followed the familiar pattern of many great comets, beginning as a faint, distant object that gradually brightened as it approached the sun. But what made Neowise special was its timing and accessibility. As the comet reached its closest approach to the sun, in early July 2020, it emerged from the solar glare as a magnitude 0 object, bright enough to be easily visible to the naked eye even from suburban locations with modest light pollution. The comet's dual tail structure was particularly well defined and photogenic, creating some of the most beautiful comet photographs ever captured by amateur astronomers. The blue ion tail stretched straight away from the sun, while the curved dust tail created a graceful arc that seemed to sweep across the pre-dawn sky. For observers in the northern hemisphere, Neowise provided nightly viewing opportunities throughout July 2020, becoming a welcome distraction during challenging times. What made Neowise particularly poignant was its orbital period of approximately 6,800 years. This meant that the last time this comet visited the inner solar system, human civilization was in its infancy, with no written records and only the earliest agricultural settlements beginning to form. The next time Neowise returns, our current civilization will be as ancient to future observers as the earliest human settlements are to us today. The scientific value of Neowise extended beyond its visual beauty. Infrared observations from space-based telescopes revealed details about the comet's nucleus and composition that would have been impossible to obtain from ground-based observations alone. These studies showed that Neowise was shedding water at a rate of several tons per second during its peak activity, while also releasing significant amounts of carbon dioxide and other volatiles. But perhaps no recent comet has demonstrated the unpredictable and sometimes violent nature of these cosmic visitors, quite like C/2024 G3 Atlas, which earned the designation as the Great Comet of 2025, discovered in April 2024 by the automated Atlas survey system. This comet began its journey toward the Sun as an unremarkable 19th magnitude object, far too faint to be visible except through powerful telescopes. What happened next illustrates both the spectacular potential and the fragile nature of these ancient wanderers. As C/2024 G3 Atlas approached its closest point to the Sun, it underwent dramatic brightening that exceeded all predictions. By January 2025, the comet had become bright enough to be visible during daylight hours, joining an exclusive group of only 5 comets in the past century to achieve this remarkable feat. The comet's perihelion passage, its closest approach to the Sun, brought it within 13 million kilometers of our star's surface, subjecting it to temperatures and radiation that few objects can survive intact. For a brief, glorious moment, C/2024, G3 Atlas blazed at magnitude -3.8, rivaling the brightness of Venus, and creating a spectacle visible even in broad daylight to those who knew where to look. But this close solar encounter came at a price. The intense heating and tidal forces near the Sun proved too much for the comet's nucleus to withstand. Recent observations have confirmed that C/2024 G3 Atlas has suffered significant disintegration, breaking apart under the extreme conditions near perihelion. What remains is a so-called headless wonder, a comet tail without its parent nucleus, gradually fading as the debris spreads along the comet's orbital path. This dramatic disintegration highlights an important aspect of comet behavior that we often overlook in our fascination with their beauty. These objects are fundamentally fragile, held together by weak gravitational forces, and composed largely of volatile materials that sublimate readily when heated. Many comets don't survive their close encounters with the Sun, breaking apart or completely vaporizing during their perihelion passage. The fragmentation of comets can create spectacular but short-lived displays, as we witnessed with C/2024 G3 Atlas. When a comet nucleus breaks apart, each fragment begins sublimating independently, often creating multiple tails and a much brighter overall display than the intact comet would have produced. However, this increased brightness comes at the cost of the comet's longevity, as the fragments quickly exhaust their volatile materials and fade from view. This cycle of discovery, brightening, spectacular display, and sometimes disintegration represents the natural life cycle of these cosmic visitors. Each comet that ventures into the inner solar system faces the same fundamental challenge: how to balance the spectacular sublimation that creates its beautiful display with the need to preserve enough material to survive the encounter and continue its orbital journey. The study of comet disintegration has provided valuable insights into the internal structure and composition of these objects. When comets break apart, they reveal their interior makeup, showing us layers and regions that formed under different conditions during the early solar system. These breakup events essentially provide natural cross-sections through pristine solar system materials, offering glimpses into processes that occurred billions of years ago. The patterns of comet behavior become even more fascinating when we consider the different families and types of these cosmic wanderers. Each group tells its own story about the formation and evolution of our solar system, revealing clues about the processes that shape the worlds we know today. Short-period comets, those completing their orbits in less than 200 years, tend to follow more predictable patterns. They've made multiple passages through the inner solar system, gradually losing their most volatile materials with each encounter. This makes them somewhat less spectacular than their long-period cousins, but also more reliable in their behavior. Astronomers can track these comets across multiple apparitions, studying how they change over time and learning about the processes that govern comet evolution. Take Comet Encke, for example, which holds the record for the shortest known orbital period of any comet at just 3 1/3 years. This frequent visitor has been observed through dozens of returns, providing astronomers with an unprecedented opportunity to study how repeated solar heating affects a comet's structure and composition. Each passage strips away a little more of Encke's volatile materials, and astronomers estimate that this comet may completely exhaust its ices within the next few thousand years, leaving behind only a dark, rocky remnant. This process of gradual depletion affects all periodic comets, though at different rates depending on their size, composition, and orbital characteristics. Some comets show dramatic changes from one apparition to the next, developing new active regions or losing old ones as their surface evolves. Others maintain remarkably consistent behavior across multiple returns, suggesting a more homogeneous internal structure. The Comets family of comets represents perhaps the most dramatic example of comet evolution in action. These objects are fragments of a single, enormous comet that broke apart centuries or millennia ago, with pieces continuing to follow similar orbits that bring them extremely close to the Sun. Many Kreutz comets are discovered only hours before they either round the Sun successfully or are completely vaporized by the intense solar radiation. The Solar and Heliospheric Observatory spacecraft has discovered thousands of these sun-grazing comets, most of which are completely destroyed during their close solar encounters. These tiny fragments, often no larger than a few meters across, create brief flashes of brilliance before vanishing forever into the solar atmosphere. They represent the final act in the long drama of comet evolution, the ultimate fate that may await all comets that venture too close to our star's destructive embrace. But not all comet encounters with the Sun end in destruction. Some comets possess the size and structural integrity to survive multiple close passages, gradually evolving into what astronomers call dormant or extinct comets. These objects have exhausted most of their volatile materials, leaving behind cores that resemble asteroids more than the active comets they once were. The boundary between comets and asteroids becomes blurred when we examine these dormant objects. Some asteroids in the inner solar system may actually be extinct comet nuclei, their true nature hidden beneath layers of dark, processed material accumulated over millions of years of solar exposure. Occasionally, these sleeping giants can reawaken if impacts or internal heating expose fresh volatile materials, suddenly sprouting tails and returning to active comet behavior. This evolutionary pathway helps explain some of the strange hybrid objects astronomers have discovered in recent years. Objects like 3200 Phaethon, which follows an asteroid-like orbit but shows brief periods of activity that suggest comet-like behavior. These transitional objects provide important insights into the processes that transform active comets into inert rocky bodies over cosmic timescales. The study of comet nuclei has been revolutionized by spacecraft missions that have visited these objects up close. Each mission has revealed new surprises about the diversity and complexity of comet structure. The Rosetta mission's encounter with Comet 67, P. Churyumov-Gerasimenko, showed us a world of incredible geological complexity, with distinct layers, cliff faces, and active regions that create a landscape as varied as any planet. The images returned by Rosetta revealed that comet nuclei are far from the simple dirty snowballs once envisioned by astronomers. Instead, they appear to be complex layered structures that record the history of their formation and evolution. Some regions show evidence of seasonal changes, with different areas becoming active as the comet's rotation exposes them to varying amounts of sunlight during its orbital journey. The surface of 67P displayed a remarkable variety of terrains, from smooth, dust-covered plains to rugged, rocky outcrops that suggested different formation processes or evolutionary histories. Some areas showed signs of past activity, with pits and depressions that may have formed when subsurface ice deposits sublimated and caused the overlying material to collapse. Perhaps most surprisingly, Rosetta discovered that the comet's nucleus appeared to be composed of two distinct lobes connected by a narrow neck, suggesting that 67P might actually be a contact binary, formed when two separate objects gently collided and stuck together. This discovery has important implications for our understanding of how comets form and evolve, suggesting that many of these objects may have complex histories involving multiple accretion events. The organic compounds detected by the Philae lander on 67P's surface have provided tantalizing clues about the role comets may have played in the development of life on Earth. Among the 16 organic compounds identified, 4 had never before been detected on a comet, including acetamide and methyl isocyanate, which are important building blocks for more complex biological molecules. These discoveries have reignited interest in the panspermia hypothesis, the idea that life or its precursor molecules might have been distributed throughout the solar system by comets and asteroids. While we now know that comets alone cannot account for all the water in Earth's oceans, they may still have contributed important organic compounds that helped kickstart the chemical processes that eventually led to life. The isotopic composition of comet materials provides another window into the early solar system's conditions. Different isotopes of elements like hydrogen, carbon, and nitrogen preserve information about the temperature and chemical environment where these materials first condensed from the solar nebula. By analyzing these isotopic signatures, scientists can reconstruct the thermal history of different regions of the early solar system and understand how materials were transported and mixed during planetary formation. Some comets show isotopic signatures that suggest they formed in the very coldest regions of the outer solar system, preserving materials that condensed at temperatures approaching absolute zero. Others display evidence of having been heated or processed, possibly through radioactive decay or collisions with other objects. This diversity reflects the complex and dynamic nature of the early solar system, where materials were constantly being moved, mixed, and modified by gravitational interactions and other processes. The relationship between comets and meteor showers provides another fascinating aspect of these objects' influence on our planet. Many of the meteor showers we observe throughout the year are caused by Earth passing through debris trails left behind by comets during their previous passages through the inner solar system. The Perseids in August, the Geminids in December, and the Leonids in November all result from our planet encountering particles shed by specific comets as they rounded the Sun. These meteor showers represent a gentle but constant rain of comet material onto Earth's atmosphere, delivering thousands of tons of extraterrestrial material to our planet each year. While most of these particles are tiny, no larger than grains of sand, they carry with them the same ancient materials that make up the comet nuclei themselves, providing scientists with samples of early solar system materials that they can study in terrestrial laboratories. The timing and intensity of meteor showers can vary dramatically from year to year, depending on how Earth's orbit intersects with the evolving debris streams left by their parent comets. Some years produce spectacular displays with hundreds of meteors per hour, while others yield only modest activity. These variations reflect the complex orbital mechanics that govern how comet debris spreads along the parent object's orbital path over time. Occasionally, Earth encounters unusually dense concentrations of comet debris, producing meteor storms that can generate thousands of visible meteors per hour. These rare events, like the Leonid storms of 1833, 1866, and 1966, demonstrate the incredible amount of material that comets can shed during their active phases and highlight the dynamic relationship between these ancient wanderers and our home planet. The gravitational influence of the giant planets plays a crucial role in determining which comets we see and when they appear in our skies. Jupiter, in particular, acts as both a shepherd and a destroyer of comets, capturing some objects into short-period orbits while ejecting others completely from the solar system. This gravitational sculpting has shaped the current population of comets and continues to influence their distribution and behavior. Some comets experience close encounters with Jupiter that dramatically alter their orbits, transforming long-period visitors from the Oort cloud into short-period members of the Jupiter family of comets. These captured objects often show evidence of their violent gravitational encounters, sometimes breaking apart or developing unusual activity patterns as a result of the tidal stresses they experienced during their close approach to the giant planet. The study of these gravitational interactions has provided important insights into the early history of our solar system, particularly during a period known as the Late Heavy Bombardment, when the giant planets may have migrated significantly from their original positions. This planetary migration would have scattered countless comets and asteroids throughout the solar system, potentially delivering water and organic compounds to the inner planets during a crucial period in their development. Computer simulations of this early dynamical evolution suggest that the current populations of comets in the Kuiper Belt and Oort cloud are the surviving remnants of much larger populations that existed during the solar system's youth. Most of these ancient objects were either ejected into interstellar space or captured by the sun and planets, leaving behind only a small fraction of the original comet population that we can observe today. The discovery of interstellar comets has opened an entirely new chapter in comet science, providing our first opportunities to study objects that formed around other stars Oumuamua, discovered in 2017, and Comet 2 Borisov, found in 2019, represent visitors from beyond our solar system that offer unique insights into planetary formation processes around other stars. These interstellar visitors follow hyperbolic trajectories that carry them past our sun and back into the depths of space, never to return. Their brief passages through our solar system provide only limited opportunities for detailed study, but even these fleeting encounters have yielded important information about the diversity of planetary formation processes throughout our galaxy. Comet 2 Borisov, in particular, showed remarkable similarities to comets from our own solar system, suggesting that the processes that create these objects may be universal features of planetary system formation. Its composition and behavior closely matched what astronomers expected from a typical long-period comet, indicating that the basic physics and chemistry of comet formation may be the same throughout the galaxy. The study of these interstellar visitors has also highlighted the incredible journey that brought them to our solar system. These objects have traveled through interstellar space for millions or billions of years, surviving the harsh radiation environment and occasional gravitational perturbations that characterize the space between stars. Their successful arrival in our solar system represents an almost unimaginable triumph of cosmic endurance. The search for more interstellar comets continues as astronomers develop better techniques for detecting these rare visitors. Advanced survey telescopes like the upcoming Vera C. Rubin Observatory may discover dozens of interstellar objects each year, providing a steady stream of visitors from other stellar systems that we can study and compare with our own solar system's comet population. The future of comet science holds tremendous promise as new technologies and missions prepare to revolutionize our understanding of these ancient objects. Planned spacecraft missions will attempt to return samples of comet material to Earth, providing scientists with pristine examples of early solar system materials that they can analyze using the most sophisticated laboratory techniques available. These sample return missions represent the next major step in comet exploration, building on the successes of previous spacecraft encounters to bring actual pieces of these cosmic time capsules back to Earth for detailed study. The scientific return from such missions could be extraordinary, providing insights into the formation of our solar system that would be impossible to obtain through remote observations alone. The technological challenges of intercepting and sampling these fast-moving objects are considerable, requiring precise navigation and innovative collection techniques. But the scientific rewards justify these efforts, as comet samples could answer fundamental questions about the origin of water and organic compounds on Earth, the formation processes that created our solar system, and the conditions that existed during the earliest phases of planetary development. As we continue to study these magnificent cosmic wanderers, each new discovery adds another piece to the puzzle of our solar system's history and our own origins. The story of comets is ultimately the story of how simple ingredients scattered throughout the early solar nebula eventually combined to create the complex life-bearing world we call home. Advanced ground-based observatories and space telescopes are revealing new details about comet composition with each passing year. Spectroscopic analysis allows astronomers to identify specific molecules in comet atmospheres, creating detailed chemical inventories of these ancient objects. These observations have revealed that comets contain far more complex chemistry than originally suspected, with some objects showing evidence of prebiotic molecules that may have been crucial for the emergence of life. The seasonal variations in comet activity provide another fascinating aspect of their behavior. As a comet rotates during its journey around the Sun, different regions of its nucleus are exposed to varying amounts of solar heating. This creates distinct patterns of activity that can change dramatically over periods of hours or days. Some areas of a comet nucleus remain dormant for most of the orbital period, only becoming active when the right combination of seasonal heating and subsurface ice exposure occurs. These activity patterns have revealed that comet nuclei possess remarkably diverse internal structures. Some regions appear to be rich in volatile materials that sublimate readily when heated, while others consist primarily of rocky material that remains largely unchanged throughout multiple solar encounters. This heterogeneous composition suggests that comets formed through complex accretion processes that combined materials from different regions of the early solar system. The role of dust in comet evolution deserves special attention because it profoundly influences how these objects interact with solar radiation. The dark dust coating that develops on comet surfaces acts like a thermal blanket, insulating the underlying ice and controlling the rate at which volatile materials can escape. This creates a feedback mechanism where the comet's own dust production influences its future activity levels. When dust particles are ejected from a comet nucleus, they don't simply drift away into space. Instead, they follow complex trajectories influenced by radiation pressure, solar wind, and the comet's own gravity. Larger particles tend to remain closer to the nucleus, while smaller ones are swept away more rapidly. This size-sorting process creates the characteristic structure of comet tails, with different particle sizes contributing to different regions of the visible display. The interaction between comet dust and the solar wind creates some of the most beautiful phenomena in our solar system. As charged particles from the Sun encounter the ionized gases in a comet's coma, they create spectacular light shows that can extend for millions of kilometers through space. These interactions are similar to the processes that create Earth's auroras, but on a much grander scale and in the vacuum of space rather than in a planetary atmosphere. The magnetic properties of comets have provided surprising insights into conditions in the early solar system. Recent spacecraft missions have found that many comet nuclei lack significant magnetic fields, suggesting that magnetic forces may not have played a major role in the initial formation of these objects. This discovery has important implications for understanding how the solar nebula collapsed and condensed into the solid bodies we observe today. The temperature variations that comets experience during their orbital journeys are truly extreme. At their farthest distances from the Sun, comet nuclei exist in environments colder than anything found naturally on Earth, with temperatures approaching the cosmic background radiation level of just a few degrees above absolute zero. Yet during their closest solar approaches, these same objects can experience surface temperatures hot enough to melt lead. This thermal cycling subjects comet nuclei to enormous stresses that can cause fracturing, splitting, and sometimes complete disintegration. The repeated expansion and contraction of different materials within the nucleus creates internal pressures that can build up over many orbital cycles before being suddenly released in dramatic fragmentation events. The study of comet fragment families has revealed important information about the internal structure of these objects. When comets break apart, the resulting fragments often display very different activity levels and compositions, suggesting that the original nucleus contained distinct regions with varying volatile content. Some fragments may be rich in water ice, while others contain more exotic frozen gases or predominantly rocky material. The orbital dynamics of comet fragments provide natural experiments in celestial mechanics. As fragments separate from their parent nucleus, they follow slightly different orbital paths that gradually diverge over time. By tracking these separating fragments, astronomers can study how small gravitational and non-gravitational forces affect the motion of objects in the solar system. Non-gravitational forces play a particularly important role in comet orbital evolution. As volatile materials sublimate from a comet's surface, they create tiny rocket-like jets that can slowly alter the object's trajectory over many orbital periods. These effects are cumulative and can eventually cause significant changes in a comet's orbit, sometimes shifting objects between different dynamical families, or even ejecting them from the solar system entirely. The asymmetric nature of comet outgassing creates these non-gravitational accelerations in unpredictable ways. If a comet nucleus rotates in such a way that its most active regions face the Sun during specific parts of its orbit, the resulting gas jets can either speed up or slow down the comet's orbital motion. Over many orbital cycles, these small effects can accumulate into major orbital changes. The discovery of active asteroids has blurred the traditional distinction between comets and asteroids in fascinating ways. These objects follow asteroid-like orbits in the inner solar system, but occasionally display comet-like activity, sprouting temporary tails and comas when conditions are right. This behavior suggests that the solar system contains many more ice-bearing objects than previously recognized. Some active asteroids may be dormant comet nuclei that have been reactivated by impacts or internal heating. Others might be asteroids that contain small amounts of volatile materials in protected subsurface reservoirs. The study of these hybrid objects is providing new insights into the distribution of water and other volatile materials throughout the solar system. The thermal evolution of small bodies in the solar system has created a complex population of objects with varying degrees of volatile content. Objects that formed in the coldest regions of the solar system retained their full complement of ices, while those that experienced heating lost varying amounts of their volatile materials. This thermal processing created the spectrum of objects we observe today, from highly active comets to completely dry asteroids. The role of organic compounds in comet evolution extends beyond their potential importance for astrobiology. These complex molecules can act as binding agents that help hold comet nuclei together, creating a kind of cosmic cement that gives these fragile objects more structural integrity than pure ice alone would provide. The polymerization of organic compounds under the influence of cosmic radiation may gradually strengthen comet nuclei over long periods of time. The radiation environment of interplanetary space subjects, comets, surfaces to constant bombardment by high-energy particles that can break down complex molecules and create new chemical compounds. This space weathering process gradually modifies the composition of comet surfaces, creating layers of processed material that may be quite different from the pristine interior composition. Understanding space weathering effects is crucial for interpreting observations of comet composition, because the materials we can observe spectroscopically represent only the outermost layers of these objects. The true bulk composition of comet nuclei may be significantly different from what we can measure using remote sensing techniques. The search for amino acids and other prebiotic molecules in comets continues to yield intriguing results. These compounds are remarkably stable in the cold vacuum of space, allowing them to survive for billions of years in comet nuclei. When comets are heated during their solar approaches, these organic compounds can be released into space, where they become available for spectroscopic detection. The delivery of organic compounds to the early Earth by comets and asteroids may have provided crucial ingredients for the development of life. While the exact mechanisms by which these materials could have been incorporated into early biological systems remain unclear, the presence of complex organic chemistry in comets demonstrates that the building blocks of life are widespread throughout the solar system. The isotopic signatures of organic compounds in comets provide clues about the environments where these molecules first formed. Some isotopic ratios suggest formation in very cold conditions, possibly in interstellar space, before the solar system formed. Others indicate processing at higher temperatures, perhaps in the inner regions of the solar nebula, before being transported outward and incorporated into comet nuclei. The diversity of isotopic signatures found in different comets suggests that these objects sample materials from many different regions of the early solar system. This makes comets valuable probes of solar system formation processes, as each object carries information about the specific conditions that existed, where and when it formed. The connection between comets and the zodiacal light provides another example of how these objects continue to influence our solar system long after their active phases have ended. The zodiacal light, that faint glow visible along the ecliptic plane before dawn and after sunset, is created by sunlight scattering off dust particles left behind by comets and asteroids throughout the inner solar system. This interplanetary dust cloud represents the accumulated debris from millions of years of comet activity. Every time a comet passes through the inner solar system, it leaves behind a trail of particles that gradually spread throughout the orbital region. Over cosmic timescales, this process has created a tenuous but detectable dust disk that extends throughout the planetary region. The study of interplanetary dust particles collected by high-altitude aircraft and spacecraft has provided direct samples of comet material for laboratory analysis. These tiny particles, often called cosmic dust or micrometeorites, preserve pristine examples of early solar system materials that can be studied using the most advanced analytical techniques available. The analysis of cosmic dust has revealed remarkable preservation of pre-solar grains, materials that actually predate the formation of our solar system. These ancient particles formed in the atmospheres of dying stars, or in the shock waves of stellar explosions, carrying with them isotopic signatures that record stellar nucleosynthesis processes occurring billions of years ago. The presence of pre-solar materials in comets indicates that these objects incorporated some of the oldest solid materials in our galaxy. This makes comets repositories not just of early solar system materials, but of truly ancient stellar debris that provides information about galactic chemical evolution over cosmic timescales. The future exploration of comets will likely involve increasingly sophisticated missions designed to study these objects in unprecedented detail. Proposed concepts include spacecraft that would accompany comets throughout their entire orbital cycles, monitoring changes in activity and composition as they travel from the cold outer solar system into the heated inner regions and back out again. Long-duration comet monitoring missions would provide invaluable data about the seasonal evolution of comet activity and the internal structure of these objects. By observing how different regions of a comet nucleus respond to changing solar illumination conditions, scientists could create detailed maps of subsurface ice distribution and composition. The technology for landing on and operating on comet surfaces continues to advance, building on the lessons learned from the Philae lander mission. Future surface missions might deploy networks of small landers that could monitor comet activity from multiple locations simultaneously, providing comprehensive coverage of how these dynamic objects respond to solar heating. Drilling and sampling technologies are being developed that could penetrate deep into comet nuclei, accessing pristine materials that have never been exposed to solar heating or space weathering. These subsurface samples would provide the most accurate information possible about the original composition of early solar system materials. The engineering challenges of operating spacecraft and instruments in the harsh comet environment are considerable but not insurmountable. The low gravity, extreme temperature variations, and active outgassing of comets create unique operational constraints that require innovative solutions and robust spacecraft designs. As our understanding of comet behavior improves, mission planners are developing increasingly sophisticated strategies for studying these objects safely and effectively. Advanced modeling techniques allow scientists to predict comet activity patterns and plan observations during optimal conditions for scientific data collection. The international cooperation that has characterized many recent comet missions demonstrates the global scientific interest in these objects and the benefits of sharing resources and expertise for complex space exploration projects. Future comet missions will likely continue this tradition of international collaboration, combining the strengths of different space agencies and research institutions. The scientific return from comet exploration continues to exceed expectations, as each new mission reveals unexpected aspects of these ancient objects. The complexity and diversity of comet behavior suggests that many more surprises await discovery as we develop better techniques for studying these cosmic time capsules. The story of comets represents one of the most compelling narratives in planetary science, connecting the formation of our solar system to the potential origins of life on Earth. As we continue to explore these magnificent objects, we deepen our understanding of our own cosmic heritage and our place in the grand sweep of solar system evolution. The gentle dance of these ancient wanderers through our solar system continues to unfold before our eyes, each passage bringing new opportunities for discovery and wonder. In their brilliant tales and spectacular displays, we see not just beautiful celestial phenomena, but messages from the very dawn of time, carrying stories of how simple cosmic ingredients combined to create the rich and complex world we inhabit today. These cosmic messengers remind us that we are part of something much larger than ourselves, participants in an ongoing story of stellar birth and death, planetary formation, and the emergence of complexity from simplicity. Every comet that graces our skies connects us to the deepest mysteries of existence, inviting us to contemplate our origins and our destiny among the stars. The intricate choreography of comet discovery reveals patterns that have remained consistent throughout human history, yet each new find brings its own unique surprises. Modern automated sky surveys have revolutionized our ability to detect these distant visitors, scanning vast areas of sky nightly with digital eyes far more sensitive than any human observer could achieve. These robotic sentinels have discovered thousands of new comets, from faint wisps, barely detectable even with powerful telescopes, to brilliant specimens that announce themselves with spectacular displays visible across entire hemispheres. The Catalina Sky Survey, Linear, and Neowise programs represent the cutting edge of comet hunting technology, using sophisticated algorithms to identify moving objects against the fixed backdrop of stars. These systems can detect comets years or even decades before they reach peak brightness, providing astronomers with unprecedented opportunities to study their evolution throughout their entire approach to the inner solar system. Yet amateur astronomers continue to play crucial roles in comet discovery. Armed with dedication, patience, and increasingly sophisticated equipment, the thrill of being the first human to spot a new cosmic visitor remains one of astronomy's most accessible adventures. Many significant comets still bear the names of their amateur discoverers, testament to the democratic nature of cosmic exploration, where curiosity and persistence matter more than institutional affiliation. The naming conventions for comets reflect both their discovery circumstances and our evolving understanding of these objects. Each comet receives a formal designation that encodes the year of discovery, the half-month period when it was found, and a sequential number indicating its order of discovery during that period. This systematic approach ensures that every comet receives a unique identifier, even as the numbers grow into the thousands with modern survey capabilities. But beyond these technical designations, the most memorable comets earn popular names that capture public imagination. Great comets like Hyakutake, McNaught, and Lovejoy become household words, their names forever associated with spectacular celestial displays that inspire wonder across cultures and generations. These names carry forward the tradition of comet nomenclature that stretches back centuries, connecting modern discoveries to the long history of human fascination with these cosmic wanderers. The prediction of comet brightness remains one of the most challenging aspects of comet science, combining precise orbital mechanics with the unpredictable physics of sublimation and dust production. Even experienced comet observers speak of these objects as notoriously fickle, capable of exceeding expectations by orders of magnitude or disappointing observers with unexpectedly dim performances. The factors that determine comet brightness are numerous and interconnected in complex ways. The size of the nucleus obviously matters, but so does its composition, the orientation of its rotation axis, the seasonal distribution of active regions, and the accumulated effects of previous solar encounters. A small comet with a high proportion of volatile materials might outshine a much larger object composed primarily of refractory dust and rock. Surface activity patterns add another layer of complexity to brightness predictions. Some comets display remarkably consistent behavior from one apparition to the next, while others undergo dramatic changes that can catch even experienced observers off guard. The development of new active regions or the sudden exposure of buried ice deposits can cause spectacular brightness surges that transform modest comets into headline-grabbing spectacles. The seasonal effects of comet rotation create fascinating variations in activity levels that unfold over periods of hours, days, or months, depending on the object's rotational period and the distribution of active regions across its surface. These variations can create pulsing brightness changes or dramatic jets of material that sweep across the sky like cosmic lighthouse beams as the nucleus rotates. Some comets exhibit what astronomers call outburst behavior, sudden increases in brightness that can occur at any point in their orbital journey. These events may result from internal heating, impact events, or the sudden exposure of fresh volatile materials previously buried beneath the surface crust. Outbursts can increase a comet's brightness by factors of hundreds or thousands, transforming invisible distant objects into spectacular naked-eye phenomena almost overnight. The study of comet outbursts has revealed important information about the internal structure and evolution of these objects. The timing, duration, and intensity of outburst events provide clues about subsurface processes that would otherwise remain hidden from observation. Some comets show regular patterns of outburst activity that suggest systematic changes in their internal structure or composition. The photographic documentation of comets has evolved dramatically, from the earliest attempts to capture these moving objects on glass plates to today's sophisticated digital imaging systems. Modern astrophotographers can create stunning portraits of comets that reveal details invisible to the naked eye, from delicate structural features in the tail to subtle color variations that reflect different chemical processes occurring in the coma. Time-lapse photography has become particularly valuable for studying comet behavior, allowing observers to compress hours or days of activity into brief sequences that reveal the dynamic nature of these objects. The rotation of the nucleus, the evolution of jet structures, and the response to changing solar illumination conditions all become visible through these accelerated observations. The color photography of comets reveals a palette of hues that reflects the complex chemistry occurring at their atmospheres. The blue-green glow of the inner coma results from carbon compounds energized by solar radiation, while the yellow-white dust tail reflects sunlight like countless microscopic mirrors. The blue ion tail glows with its own ethereal light, as electrically charged gas molecules emit photons at specific wavelengths determined by their atomic structure. Spectroscopic analysis allows astronomers to decode these colors into detailed chemical inventories of comet composition. Each element and molecule produces characteristic spectral lines that serve as fingerprints identifying their presence in the comet's atmosphere. These observations have revealed that comets contain an astonishing variety of chemical compounds, from simple water and carbon dioxide to complex organic molecules that may have played crucial roles in the development of life. The seasonal progression of comet development creates a predictable, yet endlessly variable sequence of changes as these objects approach and recede from the Sun. The initial detection phase often reveals nothing more than a fuzzy star slightly out of focus compared to the sharp stellar background. Experienced observers learn to recognize these subtle signs that distinguish a distant comet from a faint galaxy or nebula. As the comet continues its inward journey, the first signs of activity typically appear as a gradual swelling of the apparent size and a softening of the central condensation. This marks the beginning of coma formation as the most volatile materials begin to sublimate in response to increasing solar heating. The coma may remain nearly spherical during these early stages, showing little evidence of the spectacular tail development that will follow. The emergence of the first tail usually occurs quite suddenly from an observer's perspective, though the physical processes have been building gradually over weeks or months. The tail may appear first as a faint extension on one side of the coma, often visible only in long exposure photographs before becoming apparent to visual observers. The development of distinct dust and ion tails creates some of the most beautiful and scientifically informative aspects of comet displays. The dust tail, with its characteristic curve and yellowish color, provides information about the size, distribution, and composition of solid particles ejected from the nucleus. The straighter, bluer ion tail reveals details about the solar wind conditions and the magnetic field environment through which the comet is traveling. The interaction between solar wind and comet atmospheres creates some of the most dynamic phenomena observable in our solar system. As the stream of charged particles from the Sun encounters the expanding coma of neutral gas molecules, it creates a bow shock similar to the wake of a boat moving through water. This interaction region can extend for millions of kilometers around the comet, creating a vast magnetosphere that influences the behavior of both the solar wind and the comet's own atmosphere. The magnetic field carried by the solar wind can become draped around the comet's coma, creating complex field configurations that channel the flow of ionized gas into the characteristic straight ion tail. Variations in solar wind pressure and magnetic field orientation can cause dramatic changes in tail structure over periods of hours or days, creating disconnection events where entire sections of the ion tail are swept away and reformed. These solar wind interactions have provided valuable information about conditions in interplanetary space that would be difficult to obtain through other means. Comets essentially serve as natural probes of the solar wind environment, their visible responses to changing conditions providing real-time indicators of solar activity and interplanetary magnetic field variations. The ground-based observation of comets requires careful planning and specialized techniques to capture the best possible views of these often faint and rapidly changing objects. The low surface brightness of comet tails means that dark skies are essential for visual observation, while the extended nature of these features demands wide-field telescopes and imaging systems. the timing of comet observations must account for the object's changing position relative to both the Sun and Earth, as well as the seasonal variations in viewing conditions from any particular location. A comet that provides spectacular views for observers in the Northern Hemisphere might be poorly placed for Southern Hemisphere observers, or vice versa. The geometry of Earth's orbit and the comet's trajectory determines these viewing windows, sometimes creating brief periods of optimal visibility that must be seized when they occur. The photographic challenges of comet imaging stem from the combination of the object's motion against the stellar background and the need for long exposures to reveal faint tail details. Tracking the comet's motion during extended exposures requires either specialized tracking systems or sophisticated image processing techniques to combine multiple shorter exposures while maintaining sharp comet features. The digital revolution in astronomy has made detailed comet photography accessible to amateur observers equipped with relatively modest telescopes and cameras. Modern image processing software can extract remarkable detail from comet images, revealing structural features and color variations that would have been impossible to detect using traditional photographic methods. The social media age has transformed how comet discoveries and observations are shared with the global community. Spectacular comet images can reach millions of viewers within hours of being captured, inspiring widespread interest in these cosmic visitors and encouraging more people to venture outside and look up at the night sky. The educational impact of bright comets extends far beyond the astronomical community, providing natural teaching opportunities about solar system formation, orbital mechanics, and the history of scientific discovery. Schools and planetariums around the world use comet appearances as focal points for broader discussions about space science and our place in the cosmos. The cultural significance of comets continues to evolve as our scientific understanding grows, but these objects retain their power to inspire awe and wonder across all segments of society. From ancient cultures that saw omens in comet appearances to modern observers who understand their role as messengers from the early solar system, comets remain among the most emotionally compelling objects in the night sky. The amateur astronomy community has embraced comet observation as one of the most rewarding aspects of their hobby, combining the thrill of discovery with the satisfaction of contributing meaningful scientific observations. Visual observers maintain detailed records of comet brightness, tail length, and structural changes that complement professional astronomical studies and provide valuable long-term data sets for comet behavior analysis. The sketching tradition in amateur astronomy finds particular expression in comet observation, where the subtle details and rapid changes in these objects challenge observers to develop keen observational skills and artistic techniques. These hand-drawn records capture aspects of comet appearance that photographs sometimes miss, preserving subjective impressions of color, contrast, and structural detail that contribute to our overall understanding of comet behavior. The periodic nature of some comets has created communities of observers who maintain decades-long vigils, documenting changes in familiar objects across multiple apparitions. These long-term studies have revealed evolutionary trends in comet behavior that would be impossible to detect through shorter observation periods, contributing crucial data about how these objects age and change over cosmic timescales. The unpredictability of comet discoveries means that the next great comet could appear at any time, potentially providing the astronomical event of a generation with little advance warning. This possibility keeps comet enthusiasts alert and prepared, their telescopes ready to capture whatever celestial surprise the cosmos might deliver. The technological advancement in comet detection and study continues to accelerate, with new instruments and techniques constantly expanding our ability to understand these ancient objects. Adaptive optics systems allow ground-based telescopes to achieve space-like image quality for comet observations, while sophisticated spectrographs can detect trace amounts of exotic molecules in comet atmospheres. The coordination between professional and amateur observers has become increasingly sophisticated, with real-time communication networks allowing rapid dissemination of comet discoveries and observational data. This collaborative approach maximizes the scientific return from comet apparitions by ensuring comprehensive coverage from observers around the world. The future of comet science promises even more exciting discoveries as our observational capabilities continue to improve and our theoretical understanding becomes more sophisticated. Each new comet provides opportunities to test and refine our models of solar system formation and evolution, while unexpected discoveries continue to challenge our assumptions about these ancient objects. The legacy of great comets lives on in the memories and records of those who witnessed their passages, creating a continuous thread of human experience that connects us to observers throughout history who marveled at these same types of celestial phenomena. In contemplating these cosmic visitors, we participate in an unbroken tradition of wonder and curiosity that defines our species' relationship with the universe around us. The gentle majesty of comets as they sweep through our solar system continues to remind us of the dynamic and interconnected nature of the cosmic environment we inhabit. These ancient wanderers carry within them not just the physical materials of the early solar system, but also the capacity to inspire, educate, and humble us as we contemplate the vast scales of space and time that govern our cosmic home. As we delve deeper into the mechanics of how these cosmic visitors interact with our planet, we discover that comets have been silently shaping Earth's environment in ways both subtle and profound throughout our planet's entire history. The gravitational dance between Earth and passing comets creates intricate patterns of influence that extend far beyond the spectacular visual displays we observe in our night skies. The orbital resonances that develop between Earth and periodic comets can persist for thousands of years, creating predictable cycles of close approaches that gradually evolve over cosmic timescales. These resonant relationships mean that some comets return to Earth's vicinity at regular intervals, their orbits synchronized with our planet's journey around the Sun in mathematical harmonies that would make ancient astronomers weep with wonder. Consider how the debris streams left by these celestial visitors continue to intersect Earth's orbital path long after the parent comets have faded from view. Every August, our planet plunges through the debris trail left by Comet Swift-Tuttle, creating the spectacular Perseid meteor shower that lights up summer skies with dozens of shooting stars per hour. These meteoric displays represent direct physical contact with comet material, tiny fragments of ancient ice and dust burning up in our atmosphere at speeds of over 70 kilometers per second. The Geminids in December tell an even more intriguing story, as they appear to originate from an asteroid-like object called 3200 Phaethon that may actually be the rocky remnant of an ancient comet nucleus. This discovery has blurred the traditional boundaries between asteroids and comets, revealing that our solar system contains a continuum of objects with varying degrees of volatile content and activity. The quadrantids, Lyrids, Eta Aquariids, and dozens of other annual meteor showers each trace their origins to specific comets, creating a year-round calendar of cosmic encounters that connect us directly to these ancient wanderers. The intensity and timing of these showers can vary dramatically from year to year, depending on how Earth's path intersects with the evolving debris streams and whether we encounter dense concentrations of particles or sparser regions. Some years produce meteor storms that generate thousands of visible meteors per hour, transforming the night sky into a celestial fireworks display that can be both beautiful and slightly unsettling in its intensity. The Great Leonid Storm of 1833 reportedly produced meteors at rates exceeding 100,000 per hour, creating displays so spectacular that many observers thought the stars themselves were falling from heaven. These encounters with comet debris deliver far more material to Earth than most people realize. Scientists estimate that our planet accumulates thousands of tons of cosmic dust each year, most of it originating from comets that have shed their substance throughout the inner solar system. This constant influx of extraterrestrial material means that every breath you take contains atoms that once resided in the frozen nucleus of a distant comet. The chemical analysis of collected meteor particles has revealed remarkable diversity in comet composition, with some samples containing organic compounds that may have contributed to the development of life on our planet. These microscopic messengers carry with them isotopic signatures that preserve information about conditions in the outer solar system billions of years ago, when the first solid materials were condensing from the cooling solar nebula. The role of comets in delivering water to the early Earth remains one of the most actively debated questions in planetary science. While isotopic analysis has shown that comets alone cannot account for all the water in our oceans, they may still have contributed significantly to Earth's volatile inventory during the planet's formative years. The late heavy bombardment period, roughly 4 billion years ago, may have seen countless comets and asteroids delivering water, organic compounds, and other crucial ingredients for life to the inner planets. This cosmic delivery system operated on scales that dwarf anything we can easily comprehend. Individual comet impacts during this period could have delivered the equivalent of entire lakes or small seas of water to Earth's surface. The cumulative effect of thousands of such impacts over millions of years could have fundamentally altered our planet's surface chemistry and atmospheric composition. The timing of this bombardment period coincides roughly with the earliest evidence for life on Earth, suggesting that comets may have played a crucial role not just in delivering water, but in providing the organic building blocks that made biochemistry possible. The complex carbon compounds detected in modern comets include amino acids, nucleotide bases, and other molecules that form the foundation of biological systems. Yet the relationship between comets and life extends beyond simple delivery of raw materials. The periodic impacts and near misses throughout Earth's history have also created environmental stresses that may have driven evolutionary innovation. Mass extinction events, climate changes, and atmospheric disturbances caused by comet encounters have repeatedly reshaped the biosphere, eliminating some species while creating opportunities for others to diversify and adapt. The Cretaceous impact that ended the age of dinosaurs 66 million years ago was probably caused by an asteroid rather than a comet. But similar events involving comets have undoubtedly occurred throughout Earth's history. These cosmic catastrophes serve as stark reminders that our planet exists within a dynamic and sometimes violent cosmic environment where the arrival of visitors from the outer solar system can have profound consequences for life. The study of impact craters on Earth and other planetary surfaces reveals the long history of comet and asteroid bombardment that has shaped the evolution of our solar system. While most comet impacts on Earth have been erased by geological processes, the Moon's heavily cratered surface preserves a record of the intense bombardment that characterized the early solar system. Many of these lunar craters were almost certainly created by comet impacts, their distinctive characteristics helping scientists understand the physical properties of these ancient projectiles. The ongoing threat of comet impacts continues to motivate astronomical surveys designed to detect potentially hazardous objects years or decades before they might pose a danger to Earth. While the probability of a major comet impact during any human lifetime is extremely small, the consequences of such an event would be so severe that constant vigilance is warranted. The challenge of detecting dangerous long-period comets lies in their unpredictable arrival times and the relatively short warning periods they provide. Unlike near-Earth asteroids that follow well-known orbits and can be tracked for decades in advance, a large comet from the Oort cloud might not be discovered until months or years before its closest approach to Earth. This compressed timeline would make any deflection or mitigation efforts extremely challenging with current technology. Fortunately, the vast majority of comet orbits carry them safely past Earth without posing any threat to our planet. The gravitational influence of the giant planets, particularly Jupiter, acts as a cosmic shield that deflects many potentially dangerous objects away from the inner solar system, or captures them into harmless orbits that don't intersect Earth's path. The protective role of Jupiter in our solar system extends far beyond its influence on comet trajectories. This giant planet also acts as a gravitational vacuum cleaner, capturing or ejecting countless small objects that might otherwise pose hazards to the inner planets. Computer simulations suggest that without Jupiter's protective presence, Earth would experience far more frequent impacts from comets and asteroids, possibly making the evolution of complex life much more difficult. The delicate balance of gravitational forces that maintains the current architecture of our solar system has evolved over billions of years through complex dynamical processes that we're only beginning to understand. The migration of the giant planets during the solar system's youth redistributed countless comets and asteroids, establishing the current populations we observe today in the Kuiper Belt and Oort cloud. This early period of planetary migration, sometimes called the Late Heavy Bombardment, represents one of the most violent and chaotic phases in our solar system's history. The gravitational perturbations caused by migrating planets scattered objects throughout the solar system, sending some into planet-crossing orbits, while ejecting others into interstellar space forever. The survivors of this chaotic period form the populations of small bodies we study today, each carrying within their composition and orbital characteristics clues about the processes that shaped our cosmic neighborhood. The Kuiper Belt preserves objects that formed in the outer regions of the solar system and avoided significant dynamical evolution, while the Oort cloud contains materials that were scattered outward during the period of planetary migration. The chemical gradients that existed in the early solar nebula created systematic variations in composition with distance from the forming sun, and these signatures are still preserved in the comet populations we observe today. Objects that formed closer to the sun tend to be depleted in the most volatile materials, while those that condensed in the coldest outer regions retained their full complement of ices and organic compounds. This compositional diversity makes each comet a unique probe of early solar system conditions, carrying information about the specific time and place where it formed. By studying large numbers of comets from different dynamical families, scientists can reconstruct the thermal and chemical environment that existed throughout the solar nebula during the epoch of planetary formation. The isotopic ratios preserved in comet materials provide particularly valuable information about these early conditions, because isotopes are sensitive indicators of temperature, pressure, and chemical processing. The discovery that different comets show varying isotopic signatures suggests that the early solar system was a complex and dynamic environment where materials were constantly being mixed and redistributed by turbulent processes. Some comets show evidence of having incorporated pre-solar grains, materials that actually predate the formation of our solar system and originated in the atmospheres of dying stars or in the shock waves of stellar explosions. These ancient particles carry isotopic signatures that record stellar nucleosynthesis processes occurring billions of years before our sun began to shine. The presence of pre-solar materials in comets indicates that star formation is a messy process that incorporates debris from previous generations of stars into new stellar systems. This means that comets are repositories not just of early solar system materials, but of truly ancient galactic materials that provide information about stellar evolution and chemical processing over cosmic timescales. The study of interstellar dust particles collected from the upper atmosphere has revealed that we live in a constant rain of material from other star systems, much of it incorporated into comets and asteroids throughout our solar system's history. This ongoing exchange of material between stellar systems suggests that the chemical evolution of the galaxy is a highly interconnected process where individual stars contribute to and benefit from a vast network of material circulation. The recent discoveries of interstellar comets passing through our solar system have provided direct opportunities to study materials that formed around other stars. These visitors from interstellar space offer unique insights into planetary formation processes throughout our galaxy and help us understand whether the conditions that created our solar system are common or unusual. Oumuamua and Comet 2. I. Borisov, the first confirmed interstellar visitors, showed both similarities to and differences from objects native to our solar system. Their successful journey through interstellar space demonstrates the remarkable durability of these ancient materials and suggests that the exchange of small bodies between stellar systems may be a common process throughout the galaxy. The implications of interstellar material exchange extend beyond simple scientific curiosity to fundamental questions about the distribution of life throughout the universe. If comets and asteroids regularly travel between star systems, they could potentially carry organic compounds or even microorganisms across the vast distances that separate stellar neighborhoods. This possibility has reinvigorated interest in the panspermia hypothesis, the idea that life might spread throughout the galaxy through natural processes rather than arising independently in each suitable environment. while the survival of complex organisms during million-year journeys through interstellar space remains highly speculative. The transport of organic compounds and possibly simple microorganisms cannot be ruled out entirely. The discovery that complex organic chemistry is widespread in comets throughout our solar system suggests that the chemical ingredients for life may be common throughout the galaxy. If similar processes occur around other stars, then the building blocks of biochemistry may be distributed widely through comet populations in countless stellar systems. The philosophical implications of this cosmic connection are profound, suggesting that we may be part of a vast galactic ecosystem where materials, and possibly even life itself, flow between stellar systems on timescales measured in millions of years. This perspective places Earth and its biosphere within a much larger context of cosmic evolution and chemical processing. The continuing study of comets promises to reveal even more about these connections between our solar system and the broader galactic environment. Advanced spectroscopic techniques are beginning to detect increasingly complex molecules in comet atmospheres, expanding our inventory of the organic compounds available in these ancient objects. The development of sample return missions will provide unprecedented opportunities to analyze comet materials using the most sophisticated laboratory techniques available on Earth. These missions face enormous technical challenges in intercepting fast-moving targets and collecting samples without contaminating them. But the scientific rewards justify the complexity and expense involved. The engineering solutions required for comet sample return missions are pushing the boundaries of spacecraft design and autonomous navigation systems. The ability to intercept, match velocities with, and collect samples from objects traveling at tens of kilometers per second requires precision and reliability that exceeds most previous space missions. The scientific analysis of returned comet samples will likely revolutionize our understanding of early solar system chemistry and the processes that created the materials from which planets formed. These samples will provide ground truth for interpreting remote spectroscopic observations and may reveal unexpected aspects of comet composition that cannot be detected through telescopic studies alone. The preservation of pristine comet materials in laboratory conditions will allow detailed studies of organic chemistry, isotopic ratios, and mineral structures that formed under conditions very different from those found anywhere on Earth. These analyses may provide crucial insights into the mechanisms that concentrated and organized the raw materials that eventually became planets and life itself. The integration of comet science with broader studies of planetary formation and astrobiology creates exciting opportunities for interdisciplinary research that connects stellar evolution, planetary science, and the search for life beyond Earth. Each new comet discovery adds another piece to this vast puzzle of cosmic evolution and our place within it. As we continue to observe these magnificent cosmic wanderers, we're reminded that they represent far more than beautiful celestial displays. They are messengers from the very edge of our solar system's influence, carriers of materials and information from the earliest epochs of planetary formation, and potential contributors to the chemical processes that made life possible on Earth. The story of comets is ultimately inseparable from the story of our own existence, written in ice and dust across billions of years of cosmic evolution. In their ancient materials, we find clues to our origins. In their spectacular displays, we experience wonder and connection to the cosmos. And in their ongoing journeys, we glimpse the dynamic processes that continue to shape our solar system today. These wandering time capsules remind us that we inhabit a universe in constant motion and evolution, where materials formed in the hearts of ancient stars eventually become incorporated into planets, life, and consciousness itself. Every comet that graces our skies carries with it this profound message of cosmic interconnection, inviting us to contemplate our place in the grand story of the universe. The gentle dance of comets through our solar system will continue long after human civilization has passed into history, these ancient objects following their predetermined paths through space and time with mathematical precision. Yet for now, we have the extraordinary privilege of witnessing their passages, studying their composition, and marveling at their beauty as they transform from invisible chunks of ice into spectacular celestial phenomena in the quiet darkness of a clear night. When a comet hangs suspended in the star-filled sky with its luminous tail streaming across the heavens, we experience a direct connection to the deepest mysteries of existence. These moments of cosmic contemplation remind us that we are made of the same materials that compose these ancient wanderers. Temporary arrangements of stellar debris that have somehow achieved the remarkable ability to look up at the night sky and wonder about our origins. The comets will continue their eternal journeys, carrying their ancient secrets through the vast spaces between worlds, occasionally emerging from the darkness to remind us of the magnificent complexity and beauty of the cosmic environment we call home. In their light, we see reflected our own cosmic heritage and the continuing story of a universe that remains full of mystery, wonder, and infinite possibility. Wonder and infinite possibility. The patterns of comet behavior become even more fascinating when we consider how these ancient objects serve as natural laboratories for understanding the fundamental forces that govern our universe. Each comet's journey through the solar system creates a unique set of conditions that allow us to study physics and chemistry in environments impossible to replicate on Earth. As a comet approaches the inner solar system, it essentially becomes a massive natural experiment in sublimation physics, where solid materials transform directly into gas without passing through a liquid phase. This process occurs under conditions of near-perfect vacuum and intense radiation that would be impossible to maintain in any terrestrial laboratory. Yet comets perform these transformations effortlessly, as they have for billions of years. The temperature gradients that develop within a comet nucleus as it approaches the Sun create fascinating patterns of thermal stress and material flow. The outer layers may reach temperatures hot enough to sublimate water ice, while materials just centimeters below the surface remain frozen at temperatures hundreds of degrees colder. This creates a dynamic system where heat slowly penetrates inward while vaporized materials escape outward, carrying away thermal energy and creating the spectacular displays we observe. The mechanics of how gas escapes from a comet nucleus reveal intricate details about the internal structure of these objects. Some regions of the nucleus may be highly porous, allowing gas to escape easily through interconnected pathways, while other areas may be sealed by dense crustal layers that prevent sublimation until the internal pressure builds to explosive levels. These variations create the complex patterns of jets and active regions that make each comet unique in its behavior. The rotation of the comet nucleus adds another layer of complexity to these processes, creating diurnal cycles of heating and cooling that can dramatically alter the activity patterns over periods of hours or days. Some comets show pronounced variations in brightness and tail development as different regions rotate into and out of direct sunlight, while others maintain more constant activity levels due to their internal structure or rotational characteristics. The study of these rotational effects has revealed that many comet nuclei have highly irregular shapes, often resembling contact binaries, where two separate objects have gently collided and stuck together. This discovery has important implications for understanding how comets formed in the early solar system, suggesting that many of these objects may represent the products of low-velocity collisions between smaller building blocks. The gravitational environment around an active comet creates a complex dynamical system where escaping gas and dust interact with the nucleus's weak gravity field. Larger particles may follow ballistic trajectories that eventually return them to the surface, while smaller grains are swept away by radiation pressure and solar wind effects. This size-dependent sorting process creates distinct zones around the nucleus with different particle populations and physical conditions. The coma that develops around an active comet can extend for hundreds of thousands of kilometers, creating an atmosphere far more extensive than that of any planet in our solar system. Yet this vast envelope of gas and dust remains gravitationally bound to a nucleus that may be only a few kilometers across, demonstrating the remarkable efficiency with which small amounts of gravitational attraction can organize matter over enormous volumes. Within this extended coma, complex chemical processes occur as solar radiation breaks apart molecules and creates new compounds that never existed in the original nucleus. The ultraviolet light from the sun provides energy for photodissociation reactions that fragment water molecules, carbon dioxide, and organic compounds into reactive fragments that can recombine in unexpected ways. These photochemical processes create the distinctive colors we observe in comet atmospheres, as different molecular species emit light at characteristic wavelengths when energized by solar radiation. The green glow of the inner coma results from carbon compounds, while the blue light of ion tails comes from carbon monoxide ions and other charged species that interact directly with the solar wind. The magnetic properties of the solar wind create additional complexity in comet tail formation, as the interplanetary magnetic field becomes draped around the expanding coma and channels the flow of ionized gas into the characteristic straight ion tail. Variations in solar wind conditions can cause dramatic changes in tail structure over periods of hours, sometimes creating disconnection events where entire sections of the tail are swept away and must reform. These solar wind interactions make comets valuable probes of conditions in interplanetary space. Their visible responses to changing solar activity, providing real-time indicators of magnetic field variations and solar wind pressure fluctuations. The study of comet tail dynamics has contributed significantly to our understanding of how the solar wind interacts with planetary magnetospheres and atmospheres. The dust component of comet tails follows different physical laws than the ionized gas, responding primarily to radiation pressure from sunlight rather than magnetic forces from the solar wind. This creates the characteristic curved shape of dust tails, as particles of different sizes follow slightly different trajectories away from the nucleus. The largest particles remain close to the comet's orbital path, while the smallest grains are swept away more rapidly by radiation pressure. The size distribution of dust particles in comet tails provides information about the fragmentation processes occurring within the nucleus and the mechanisms by which solid materials are incorporated into the escaping gas flow. Spectroscopic analysis of scattered sunlight from these particles reveals their composition and physical properties, allowing scientists to infer details about the solid materials from which they originated. The temporal evolution of dust production rates throughout a comet's orbital cycle creates complex patterns of particle density along the comet's path through space. These debris trails can persist for thousands of years after the parent comet has passed, gradually spreading under the influence of planetary perturbations and radiation effects. When Earth's orbit intersects these ancient debris streams, we experience meteor showers that connect us directly to comets that may have been active centuries or millennia ago. The annual meteor shower calendar essentially represents a map of comet debris throughout the inner solar system, with each shower tracing back to a specific parent object and providing information about when and where that comet was most active. The intensity variations from year to year reflect the clumpy distribution of particles within these streams and the complex orbital mechanics that determine when Earth encounters the densest concentrations. Some meteor showers show remarkable consistency from year to year, indicating that their parent comets have distributed debris relatively uniformly along their orbital paths. Others display dramatic variations in activity, with some years producing spectacular displays, while others yield only modest numbers of visible meteors. These variations provide clues about the activity history of the parent comets and the dynamical processes that redistribute debris over time. The study of meteoroid orbits has revealed that many meteor shower particles follow highly evolved paths that differ significantly from their parent comet's current trajectory. Gravitational perturbations from the planets gradually alter these orbits over thousands of years, creating complex patterns of debris distribution that can extend far beyond the comet's original orbital path. The physical properties of meteoroids provide direct information about the composition and structure of comet nuclei, as these particles represent actual samples of comet material that we can study in terrestrial laboratories. The analysis of meteorites thought to originate from comets has revealed complex mineralogical structures that formed under conditions very different from those found in typical asteroids or terrestrial rocks. The organic compounds detected in some meteorites include amino acids, nucleotide bases, and other biologically relevant molecules that may have been delivered to the early Earth by comet impacts, while the survival of such compounds during atmospheric entry and impact processes remains questionable. Their presence in comet-derived materials demonstrates that the building blocks of biochemistry are widespread throughout the solar system. The isotopic signatures preserved in meteoroid materials provide valuable information about the conditions under which these objects formed billions of years ago. The ratios of different isotopes reflect the temperature, pressure, and chemical environment that existed in the outer solar system during the epoch of planetary formation, creating a record that can be read through sophisticated laboratory analysis. The collection of meteoroid samples during meteor showers presents significant technical challenges, as these particles typically vaporize completely during their high-speed encounters with Earth's atmosphere. However, specialized collection techniques using high-altitude aircraft and spacecraft have successfully recovered microscopic fragments that preserve useful information about comet composition. The development of increasingly sensitive analytical techniques has allowed scientists to extract remarkable amounts of information from incredibly small samples of cosmic dust. Individual particles weighing less than a microgram can now be analyzed for their isotopic composition, mineral structure, and organic content using techniques that were unimaginable just decades ago. The integration of meteoroid studies with telescopic observations of active comets creates a comprehensive picture of these objects that combines direct physical sampling with detailed remote sensing. This multifaceted approach has revolutionized our understanding of comet structure and evolution, revealing levels of complexity that were completely unexpected when comets were first studied seriously. The seasonal variations in meteoroid flux throughout the year create natural experiments in atmospheric physics as particles with different compositions and structures interact with Earth's upper atmosphere under varying conditions. The study of these interactions has provided valuable information about atmospheric chemistry and the processes that govern the entry of extraterrestrial materials into planetary atmospheres. The global distribution of meteoroid impacts creates a network of natural monitoring stations that provide continuous sampling of the interplanetary dust environment. This ongoing bombardment delivers thousands of tons of cosmic material to Earth each year, making our planet a natural collector of samples from throughout the solar system. The chemical analysis of this cosmic dust rain has revealed that Earth continuously receives materials from comets, asteroids, and possibly even interstellar sources. The isotopic signatures of these particles allow scientists to trace their origins and understand the processes that created and modified them during their journey through space. The long-term accumulation of cosmic dust in terrestrial sediments provides a record of bombardment rates and source populations that extends back millions of years. This paleontological approach to cosmic dust studies has revealed variations in bombardment intensity that may correlate with climate changes and biological events in Earth's history. The possibility that comet-derived materials have influenced terrestrial evolution extends beyond simple delivery of water and organic compounds to potential effects on atmospheric chemistry and climate patterns. Large comet impacts could have introduced significant amounts of water vapor and other greenhouse gases into the atmosphere, potentially triggering climate changes that affected the evolution of life. The study of impact craters on Earth and other planetary surfaces provides additional evidence for the long history of comet bombardment throughout the solar system. While most terrestrial craters have been erased by geological processes, the preserved examples reveal the enormous energies involved in these cosmic collisions and their potential for causing global environmental changes. The Moon's heavily cratered surface preserves a more complete record of early bombardment, with many craters almost certainly created by comet impacts during the late heavy bombardment period, approximately 4 billion years ago. The size, distribution, and morphology of these craters provide information about the population of impactors that existed during the solar system's youth. The comparative study of crater populations on different planetary surfaces reveals variations in bombardment history that reflect the complex gravitational dynamics of the early solar system. The giant planet's migration during this period scattered countless small bodies throughout the solar system, creating the impact record we observe today. The ongoing threat of comet impacts continues to motivate surveys designed to detect potentially hazardous objects before they pose a danger to Earth. While the probability of a major impact during any human lifetime is extremely small, the consequences would be so severe that constant vigilance is justified by the potential benefits of early warning. The challenge of detecting dangerous long-period comets lies in their unpredictable arrival times and the relatively short warning periods they provide. Unlike near-Earth asteroids that follow well-known orbits, a large comet from the Oort cloud might not be discovered until it's already approaching the inner solar system, leaving little time for any defensive measures. The development of more sensitive sky surveys and automated detection systems continues to improve our ability to spot distant comets years before they reach peak brightness. These early warning capabilities provide crucial lead time for detailed study of potentially threatening objects and development of mitigation strategies if needed. The technological challenges of deflecting a dangerous comet differ significantly from those involved in asteroid deflection, as the active outgassing and fragile structure of these objects create unique problems for any intervention attempts. The very processes that make comets spectacular to observe also make them difficult targets for precise manipulation. The international cooperation required for planetary defense against cosmic impacts represents one of the most compelling arguments for continued space exploration and scientific collaboration. The threat from space affects all nations equally, creating natural incentives for sharing resources and expertise in monitoring and mitigation efforts. The scientific benefits of studying potentially hazardous comets extend far beyond planetary defense to fundamental questions about solar system formation and the distribution of organic compounds throughout space. Each newly discovered object provides additional data points for understanding the populations and characteristics of these ancient remnants. The public interest generated by news of potentially dangerous comets creates valuable opportunities for science education and outreach, helping people understand both the real nature of cosmic threats and the remarkable beauty of these celestial objects. The balance between honest assessment of risks and appreciation for natural phenomena requires careful communication by scientists and educators. The historical record of comet observations throughout human civilization provides a unique perspective on how our understanding of these objects has evolved over millennia. Ancient records from China, Europe, and other cultures document comet appearances with remarkable consistency, creating an observational database that spans thousands of years. The transformation of comets from omens and portents to objects of scientific study reflects the broader evolution of human understanding about our place in the cosmos. The shift from supernatural explanations to physical models represents one of the great intellectual achievements of our species. The artistic and literary inspiration provided by comets throughout history demonstrates the profound emotional impact these objects have had on human culture. From ancient cave paintings to modern poetry, comets have served as symbols of change, beauty, and cosmic mystery that transcend purely scientific interest. The democratic nature of comet observation means that these spectacular displays are accessible to anyone with clear skies and the patience to look up. Unlike many astronomical phenomena that require specialized equipment to appreciate, great comets provide their most impressive shows to the naked eye under dark skies. The unpredictability of when the next great comet will appear adds an element of anticipation and surprise to astronomical observation that keeps both professional and amateur astronomers alert and ready. The possibility that tomorrow night might bring the discovery of a spectacular new visitor from the outer solar system continues to motivate skywatchers around the world. The photographic documentation of comets has evolved from difficult long-exposure attempts on glass plates to sophisticated digital imaging systems that can reveal details invisible to the human eye. Modern astrophotography has democratized the ability to create stunning images of these objects, allowing amateur observers to contribute beautiful and scientifically valuable documentation of comet behavior. The social media age has transformed how comet discoveries and observations are shared with the global community, creating instant worldwide networks of observers who can track and document these objects throughout their apparitions. This real-time sharing of information and images has created unprecedented opportunities for collaborative observation and public engagement. The educational impact of bright comets extends throughout society, providing natural focal points for discussions about space science, orbital mechanics, and the history of astronomical discovery. Teachers and educators around the world use comet appearances as opportunities to engage students with fundamental concepts about the solar system and scientific methodology. The inspiration provided by spectacular comet displays has motivated countless individuals to pursue careers in astronomy and space science, creating ripple effects that extend far beyond the immediate visual impact of these objects. The sense of wonder and connection to the cosmos that comets can inspire often represents a transformative experience for those fortunate enough to witness truly great displays. The legacy of famous comets lives on in the memories and records of those who observe their passages, creating continuous threads of human experience that connect us to observers throughout history who marveled at similar phenomena. In contemplating these ancient wanderers, we participate in an unbroken tradition of curiosity and wonder that defines our species' relationship with the universe. As we stand beneath the star-filled sky and gaze upon a comet's luminous tail streaming across the darkness, we experience a profound connection to both the distant past and the far future of our solar system. These moments of cosmic contemplation remind us that we are temporary arrangements of stellar materials that have somehow achieved the remarkable ability to contemplate our own origins and wonder about our place in the grand story of the universe. The gentle dance of comets through our solar system will continue long after our current civilization has passed into history. These ancient objects, following their gravitational choreography with mathematical precision through the vast spaces between worlds. Yet for now, we have the extraordinary privilege of witnessing their passages and marveling at the beauty they create as they transform from invisible chunks of primordial ice into spectacular messengers from the very edge of our cosmic neighborhood. In the quiet contemplation of a comet's passage across our night sky, we find ourselves face to face with the deepest mysteries of existence, reminded that we are part of something infinitely larger and more magnificent than our daily concerns might suggest. These wandering time capsules carry within their ancient cores not just the physical remnants of our solar system's birth, but also the capacity to inspire wonder, humility, and a profound sense of connection to the cosmic processes that created everything we know and cherish. The story of comets remains unfinished, with countless discoveries yet to be made and spectacular displays still waiting to unfold before our wondering eyes. Each new visitor from the outer darkness brings its own unique gifts of beauty and knowledge, adding another chapter to the ongoing narrative of how we came to understand our place among the stars. The stars. The profound relationship between comets and the evolution of our understanding of gravity itself reveals another layer of their scientific importance that extends far beyond their visual splendor. When Newton first formulated his laws of universal gravitation, comets provided some of the most challenging test cases for his revolutionary theory. These objects follow highly elliptical orbits that carry them from the frigid outer reaches of the solar system to scorching close encounters with the Sun, creating extreme variations in orbital velocity that perfectly demonstrate the inverse square law of gravitational attraction. The mathematical elegance of comet orbits showcases the fundamental principles that govern all motion in our universe. As a comet approaches the Sun, it accelerates dramatically under the increasing gravitational pull, reaching maximum speed at perihelion, before gradually slowing as it climbs back out toward the distant aphelion. This celestial demonstration of energy conservation occurs on scales so vast that it dwarfs any earthly example, yet follows the same physical laws that govern a ball thrown into the air. The precision with which astronomers can now predict comet returns demonstrates the extraordinary accuracy of our understanding of celestial mechanics. Halley's Comet, for instance, returns with such regularity that astronomers can calculate its position centuries into the future or trace its path thousands of years into the past. This predictive power represents one of the greatest triumphs of mathematical astronomy, transforming what once seemed like random celestial visitations into clockwork precision. Yet comets also reveal the subtle complexities that arise when ideal mathematical models encounter the messy realities of the physical universe. The outgassing that creates their magnificent displays also generates tiny rocket-like forces that gradually alter their orbits in ways that pure gravitational calculations cannot predict. These non-gravitational perturbations create slight but cumulative changes that require careful observation and analysis to understand fully. The study of these orbital perturbations has led to discoveries that extend far beyond comet science itself. The techniques developed to account for non-gravitational forces in comet motion have found applications in spacecraft navigation, satellite orbit determination, and even the detection of exoplanets around distant stars. The precision required to track comet positions has pushed the development of increasingly sophisticated observational and computational methods. The seasonal cycles that govern comet activity create natural experiments in thermal physics that would be impossible to replicate in any laboratory setting. As different regions of a comet nucleus rotate into and out of sunlight during the object's journey around the Sun, we can observe in real time how solar heating penetrates into subsurface layers and drives the complex processes of sublimation and gas escape. These thermal cycles reveal that comet nuclei possess remarkably heterogeneous internal structures, with some regions remaining dormant for most of the orbital period, while others become active as soon as they receive direct solar illumination. The patterns of jet formation and the timing of brightness variations provide detailed information about the distribution of volatile materials within these ancient objects. The discovery that many comets show distinct seasonal preferences in their activity patterns has revealed unexpected complexity in their internal architecture. Some objects become most active when their southern hemisphere faces the Sun, while others show peak activity during northern hemisphere summer. These preferences reflect the three-dimensional distribution of volatile-rich regions within the nucleus, and the complex interplay between rotation, orbital position, and subsurface heating. The spectroscopic analysis of gases escaping from active comet regions has created detailed chemical inventories that read like recipes for the early solar system. Water vapor dominates the composition of most comet atmospheres. But the presence of carbon dioxide, carbon monoxide, methane, ammonia, and dozens of more complex organic compounds reveals the rich chemistry that existed in the outer solar system during planetary formation. The relative abundances of these different molecular species provide crucial clues about the temperature and chemical conditions that existed when and where each comet formed. Objects that condensed in the coldest regions of the early solar system retain higher concentrations of the most volatile compounds, while those that experienced more heating show evidence of processing that altered their original composition. The isotopic ratios preserved in comet materials offer another window into early solar system conditions, as different isotopes of the same element behave slightly differently under various physical and chemical processes. The measurement of deuterium to hydrogen ratios, carbon isotope abundances, and nitrogen isotopic signatures provides information about nucleosynthesis processes, temperature conditions, and chemical evolution that extends back to the formation of the solar nebula itself. Some comets carry isotopic signatures that suggest they incorporated materials from interstellar space, preserving within their frozen cores actual samples of the interstellar medium that existed before our solar system formed. These ancient hitchhikers provide direct connections to stellar evolution processes occurring throughout our galaxy and demonstrate that planetary formation involves the recycling of materials across cosmic timescales. The organic chemistry detected in comet atmospheres continues to surprise scientists with its complexity and sophistication. The discovery of amino acids, the building blocks of proteins, alongside nucleotide bases that form the foundation of genetic material, suggests that the chemical pathways leading to life may be more universal than previously imagined. These findings have profound implications for astrobiology and our understanding of how life might emerge throughout the universe. The formation mechanisms that created these organic compounds remain subjects of active research and debate. Some may have formed through radiation-driven chemistry in the cold vacuum of space, while others might represent the products of aqueous alteration processes that occurred within larger parent bodies before fragmentation scattered the debris throughout the outer solar system. The preservation of delicate organic structures within comet nuclei demonstrates the remarkable stability of these frozen environments over cosmic timescales. Materials that would decompose rapidly under terrestrial conditions can survive for billions of years in the deep freeze of the outer solar system, maintaining their molecular integrity until activated by solar heating during rare visits to the inner planetary region. The role of cosmic radiation in modifying comet surface chemistry adds another layer of complexity to understanding these objects. High-energy particles from galactic cosmic rays and solar energetic particle events continuously bombard comet surfaces during their long sojourns in the outer solar system, creating new chemical compounds and altering existing molecular structures through radiolysis and other radiation-induced processes. This space, weathering gradually darkens comet surfaces and may create protective mantles that insulate underlying materials from further radiation damage. The balance between radiation-induced chemistry and the preservation of original materials creates complex layered structures that record the radiation history experienced by each object during its journey through space. The magnetic field measurements made during spacecraft encounters with comets have revealed unexpected insights into the early solar system's magnetic environment. The absence of significant magnetic fields in most comet nuclei suggests that these objects formed in regions where magnetic forces played minimal roles in the accretion process, contrasting with the strong magnetic signatures found in some meteorites from the asteroid belt. These magnetic observations provide constraints on models of solar nebula evolution and the processes that concentrated solid materials into the building blocks of planets and smaller bodies. The magnetic field patterns preserved in different solar system objects create a kind of fossil record of the magnetic conditions that existed during planetary formation. The comparative study of comet composition across different dynamical families has revealed systematic variations that reflect the diverse formation environments that existed throughout the early solar system. Jupiter family comets, originating from the Kuiper belt, show different chemical signatures than long-period comets from the Oort cloud, indicating that these populations formed under distinct conditions. These compositional differences provide crucial tests of solar system formation models and help constrain the processes that distributed materials throughout the planetary region. The chemical gradients preserved in comet populations offer direct evidence for the temperature and pressure conditions that existed at different distances from the forming sun. The discovery of hyperactive comets that produce more water vapor than can be accounted for by their visible surface area has revealed that some of these objects possess internal structures far more complex than simple solid nuclei. These objects may contain significant void spaces or highly porous regions that allow sublimation to occur throughout their interior volume, rather than just at the surface. The study of comet fragmentation events provides natural cross-sections through these ancient objects, revealing internal structures and composition variations that would otherwise remain hidden. When comets break apart, either spontaneously or due to tidal stresses during close solar approaches, they expose fresh materials that have been protected from space weathering for billions of years. The spectacular breakup of comets like Shoemaker-Levy 9, which fragmented into multiple pieces before colliding with Jupiter, demonstrated the fragile nature of these objects and provided unprecedented opportunities to study their internal composition. The different behavior of individual fragments revealed heterogeneous distributions of volatile materials and structural variations within the original nucleus. The gravitational focusing effects that occur when comets pass near massive planets create natural experiments in tidal physics that illuminate the internal structure of these objects. The stresses generated during close planetary encounters can exceed the tensile strength of weakly bound comet nuclei, leading to fragmentation events that reveal details about internal cohesion and material distribution. The study of comet dust trails using infrared space telescopes has revealed that these objects continue to shed material long after their visible activity has ceased. The thermal emission from microscopic dust particles creates detectable signatures that persist for years or decades after a comet's passage, providing information about dust production rates and particle size distributions that complement visual observations. These dust studies have revealed that comet activity often continues at low levels far from the sun, driven by sublimation of highly volatile compounds like carbon monoxide that can remain active at much greater solar distances than water ice. This extended activity helps explain why some comets develop visible comas when they're still beyond the orbit of Jupiter. The three-dimensional structure of comet dust tails, revealed through polarization studies, and multi-wavelength observations shows complex patterns of particle motion that reflect the interplay between radiation pressure, solar wind forces, and the comet's own gravity. These studies have improved our understanding of how small particles behave in the space environment and the processes that govern dust transport throughout the solar system. The connection between comet dust and the formation of planetary atmospheres represents another fascinating aspect of these objects' influence on solar system evolution. The continuous rain of comet-derived particles onto planetary surfaces may have contributed to atmospheric development and surface chemistry on worlds throughout the solar system, not just on Earth. The analysis of dust collected from comet trails by spacecraft like Stardust has provided direct samples of comet materials for laboratory study, revealing mineral structures and organic compounds that formed under conditions unlike anything found in terrestrial or lunar samples. These particles preserve records of nebular processes and early solar system chemistry that cannot be obtained through any other means. The technological challenges of collecting high-speed comet particles without destroying them have led to innovations in materials science and capture techniques that have found applications beyond space exploration. The aerogel collectors used to trap comet dust represent marvels of engineering that can decelerate particles traveling at kilometers per second while preserving their delicate internal structures. The laboratory analysis of returned comet samples has revealed isotopic anomalies and mineral structures that indicate formation under conditions of extreme cold and low pressure. Some particles show evidence of aqueous alteration that must have occurred within larger parent bodies before the materials were incorporated into comet nuclei, suggesting complex histories of processing and reprocessing. The discovery of crystalline silicate minerals in comet dust, materials that require high-temperature formation conditions, has revealed that the early solar system experienced large-scale mixing processes that transported materials from the hot inner regions to the cold outer zones where comets formed. This finding has revolutionized our understanding of nebular dynamics and material transport during planetary formation. The organic compounds found in comet dust samples include complex carbon-rich materials that may represent some of the most primitive organic matter in the solar system. The molecular structures and isotopic compositions of these compounds provide insights into the chemical processes that operated in the early solar nebula and possibly in pre-solar environments. The comparison between comet-derived organic materials and those found in carbonaceous meteorites has revealed both similarities and differences that illuminate the diverse environments where organic synthesis occurred during solar system formation. These studies are helping scientists understand the distribution and evolution of organic compounds throughout the early planetary system. The role of comets in delivering not just organic compounds but also the water that makes up Earth's oceans remains one of the most actively investigated questions in planetary science. While isotopic studies have shown that comets alone cannot account for all terrestrial water, they may still have made significant contributions during specific periods of Earth's early history. The timing of comet impacts during Earth's formation and early evolution may have been crucial for establishing the conditions that allowed life to emerge and flourish. The late heavy bombardment period, when comet and asteroid impacts peaked approximately 4 billion years ago, coincides roughly with the earliest evidence for life on our planet, suggesting possible connections between cosmic bombardment and biological origins. The environmental effects of large comet impacts on the early Earth would have been both destructive and creative, potentially sterilizing existing ecosystems, while simultaneously delivering the water and organic compounds needed for life to re-emerge in new forms. This cycle of destruction and renewal may have played crucial roles in shaping the early evolution of terrestrial life. The study of impact craters on Earth and other planetary surfaces provides evidence for the long history of comet bombardment throughout the solar system's evolution. While most terrestrial impact features have been erased by geological processes, the preserved examples demonstrate the enormous energies involved in these cosmic collisions and their potential for causing global environmental changes. The Moon's heavily cratered surface preserves a more complete record of early bombardment, with many features almost certainly created by comet impacts during the solar system's violent youth. The size distributions and morphological characteristics of lunar craters provide constraints on the populations and impact velocities of the objects responsible for this ancient bombardment. The comparative cratering records on different planetary surfaces reveal variations in bombardment history that reflect the complex gravitational dynamics of the early solar system. The migration of giant planets during the first few 100 million years scattered countless small bodies throughout the planetary region, creating the impact signatures we observe today. As we stand beneath the star-filled sky and contemplate the gentle passage of a comet across the darkness, we're witnessing far more than a beautiful celestial display. We're observing the culmination of processes that began with the collapse of an interstellar cloud over 4.5 billion years ago, continued through the chaotic epoch of planetary formation, and now unfold before our eyes as these ancient time capsules reveal their secrets through spectacular transformations triggered by our sun's warming embrace. In the luminous tail streaming behind each comet lies a story of cosmic evolution that connects the formation of the first solid materials in the cooling solar nebula to the emergence of life on Earth and the development of consciousness capable of contemplating its own origins. These wandering messengers from the edge of our solar system carry within their frozen cores not just the chemical ingredients of worlds and life, but also the capacity to inspire wonder and humility in the face of the vast scales of space and time that govern our cosmic home. The dance of comets through our solar system will continue long after our current understanding has been superseded by new discoveries and deeper insights. Yet the fundamental wonder they inspire, the connection they provide to our cosmic origins, and the beauty they create as they transform from invisible chunks of ancient ice into spectacular displays of light and motion will remain constant features of the human experience for as long as we continue to look up at the night sky and marvel at the mysteries it contains. The night sky and marvel at the mysteries it contains. The future of comet exploration promises revelations that will fundamentally reshape our understanding of these cosmic wanderers and their role in the grand narrative of solar system evolution. Advanced propulsion systems currently under development may soon allow spacecraft to accompany comets throughout their entire orbital journeys, providing unprecedented opportunities to witness the complete cycle of activation, peak activity, and dormancy that defines their existence. Imagine spacecraft equipped with nuclear electric propulsion systems capable of matching velocities with incoming long-period comets while they're still beyond the orbit of Saturn, then maintaining formation for years as these ancient objects undergo their spectacular transformation from frozen relics into active, gas-spewing phenomena. Such missions would capture the entire awakening process in exquisite detail, documenting how the first wisps of sublimating gas evolve into the magnificent tails that eventually stretch across millions of kilometers of space. The technological challenges of these extended missions pale before the scientific rewards they promise. By observing comets continuously throughout their approach to perihelion and subsequent retreat, we would finally understand the complex feedback mechanisms that govern their activity patterns. We could watch as different regions of the nucleus switch on and off in response to changing illumination conditions, mapping the three-dimensional distribution of volatile materials with unprecedented precision. Future lander missions will deploy networks of sophisticated instruments directly onto comet surfaces, creating permanent monitoring stations that can operate through multiple rotational periods and seasonal cycles. These surface observatories will measure temperature variations, gas emission rates, and seismic activity as the nucleus responds to solar heating, providing ground truth for our theoretical models of comet behavior. The engineering solutions required for these surface missions continue to evolve as we learn more about the challenging environments these objects present. The combination of extremely low gravity, active outgassing, and temperature extremes creates unique operational constraints that demand innovative approaches to spacecraft design and mission operations. Yet each successful surface mission brings us closer to understanding the detailed physics of how these ancient time capsules preserve and release their primordial contents. Advanced drilling systems under development may soon penetrate deep into comet nuclei, accessing pristine materials that have remained unchanged since the solar system's formation. These subsurface samples would provide the most accurate possible information about the original composition of the solar nebula and the processes that concentrated solid materials into the building blocks of planets and smaller bodies. The sample return missions of the coming decades will bring actual pieces of comet nuclei back to Earth for analysis using the most sophisticated laboratory instruments available. These precious samples will undergo scrutiny that extends far beyond what can be achieved through remote observations, revealing molecular structures, isotopic ratios, and organic compounds with unprecedented precision and detail. The preservation techniques required to maintain the integrity of these samples during their journey from collection to laboratory analysis represent marvels of engineering in their own right. The volatile nature of comet materials means that even slight temperature increases or exposure to contamination could destroy the very information these missions seek to obtain. Specialized storage systems must maintain near absolute zero temperatures while protecting samples from cosmic radiation and mechanical shock. The laboratory facilities being constructed to analyze these return samples incorporate clean room technologies that exceed even the most stringent pharmaceutical manufacturing standards. Every precaution must be taken to prevent terrestrial contamination of materials that may contain the most primitive organic compounds in the solar system, substances that could provide crucial insights into the chemical pathways that led to life. As we reach the end of our cosmic journey together, drifting through the ancient stories written in ice and dust across the vast expanses of space and time, we find ourselves forever changed by these wandering messengers from the very edge of our solar system. From Halley's predictable returns to the spectacular disintegration of C2024 G3 Atlas, from the pristine materials of the Oort cloud to the organic compounds that may have seeded life on Earth, we've witnessed how these magnificent time capsules connect us to the deepest mysteries of existence itself. Sweet dreams, fellow cosmic travelers, knowing that somewhere in the darkness beyond Neptune, ancient wanderers continue their eternal dance, carrying within their frozen hearts the secrets of how we all came to be among the stars.